So I'm going to talk about rational numbers in Dyalog APL. Both the design and the implementation are based on the rational numbers in J. So by rational numbers, I mean there are actually two semi-independent parts, the rational numbers themselves and prime numbers, and functions that work with prime numbers. And these are facilities in the conference edition. And all the examples that I'm going to show work, are carefully crafted to work on the conference edition without crashing. So parts of it are a little rough, and some other parts are even quite rough, but the examples I'm going to show will actually work. So some examples which we already saw in the introduction earlier this afternoon. So if you work with ordinary numbers, ordinary floating point numbers, you get floating point answers. But if you work with rational numbers, indicated by the top, the little r, and then the bottom, that's the rational number 1/2, and the rational number 1/3, you get a rational answer. And the advantage of that is that rational answers are exact. As indicated here, if you work with ordinary floating point numbers, you get a floating point answer, and then if you're using this in teaching, you're immediately having to explain what this is. Yes, and with rational numbers, you get nice, clean results. And one of the design goals of the rational numbers in Dyalog is that expressions and functions that you know and love for ordinary numbers, ordinary floating point numbers, will do the sensible thing on rational arguments. So this is the one of the functions that John mentioned in his presentation. So that's like a hook. So it's the x plus the reciprocal of y scan of 7 repetitions of the ordinary number 1, and you get a floating point answer. And if you give it a rational argument, you get a rational result. And in this case, you get a different kind of insight. So in the floating point case, you see that it's converging to the golden mean. And in the rational case, it's also converging to the golden mean, but you also see that the convergence are ratios of consecutive Fibonacci numbers, which you don't, that insight you don't see as easily in the floating point result. And of course, if you just do reduction instead of a scan, you get a single number, which is the last number you get in the scan. And as I showed earlier this afternoon, if you do it on lots, you get a rational number of many digits. It's rolling off the screen here. But we have a way to handle that in Dyalog, because the dyadic format, in this case, with a left argument of 60, says to display this number, in this case a rational number, to 60 decimal places. So that's the the golden mean to 60 decimal places. And unlike with ordinary numbers, you never run out of position for rational numbers to format. Because here it's doing you a favor by telling you that you're asking to display 60 decimal places for this floating point numbers, but you know the rest is garbage when you have floating point numbers. With rational numbers, you never have garbage. It's all good. And here's the next thing is a D-fun for computing the Hilbert matrix. And again, if you give it ordinary integer or floating point number, you get a floating point answer. And this is another result where a rational representation gives you much more insight than the floating point result. And since I prepared this beforehand, my IQ didn't drop by 50 points when I did it, and I remembered to put in the H, and you get this floating point result, and you have to look at it for a while to realize, yes, it is the identity matrix. Because when you multiply a matrix with its matrix inverse, you're supposed to get the identity matrix, and it's sort of an identity matrix for floating points. But with rationals, there's no doubt about it. And it works. Yes, again, if the Hilbert matrix is big enough, it can't do it. And it's not because the algorithm is bad. It's because there isn't enough precision to represent the result exactly. And for rationals, it works no problem. Okay. So the next thing I want to look at is integer multiplication, which is one of the determining factors of how well rational numbers perform. You know, how fast it performs. So if you have one multi-digit number and another multi-digit number, you want to multiply them together. Well, the way you learn in school is you can do an outer product, and then you shift the rows over, and then you add down. Okay, so I'm going to show the steps. So here's the outer product of these two multi-digit numbers. Happens to be base 10 here. And then you shift them over. So you shift the first row by 1, second row by 2, and so on. And then you add down. So this function d-fun p times encodes that computation. You do the outer product, shift them over, and it's a shift because I cleverly added enough zeros at the end so that when I do the rotate, it works out to be a shift, and then I add down. Yes. Oh, sorry. Yeah, so how far back do I go? Okay, so this, the function is named p times because it exactly polynomial multiplication as well as multiplication of multi-digit numbers. Okay? So if you treat the if you treat x and y as multi-digit numbers, Or if you treat them as coefficients of polynomials, it's the same. So p times. And when I first showed this to Morton, I call this convolution, because that's what computer scientists do. They say, oh, this is a convolution operation. And then Morton had the insight to say, you know, it's easier to understand if you call this polynomial multiplication rather than convolution. So that's why he's the boss and I'm just working for him. Yes. The great insight. So, and we're not finished, because when you do p times, you have these numbers that are greater than the base. So now you have to do the carry. And carry, as it happens, you can define quadrivality as a power limit. And I should say that the representation of the multi-digit numbers has the least significant digit first, so it does the carry from left to right. So that's the answer of the multiplication. So you can check that. If you do the multiplication, if you reverse these digits so that the most significant digit is first, then you get the number you expect. Okay. So this is the another name for this. This is the school method, so-called, because that's the way you learn how to do it in school, for how to multiply multi-digit numbers together. Well, it's in the 1960s. I think it was two people, I forgot the names, but they have the insight that polynomial multiplication is equivalent to you evaluate the first polynomial at a bunch of points, and you evaluate the second polynomial on the same set of points. So now you get two vector results, and then you just do the ordinary APL vector multiplication to get a vector result, and then you interpolate back to get the coefficients of the polynomial product. And the insight of these two people is that if you carefully choose the points where you evaluate to be the roots of unity, then you can do it fast. And it's called a fast Fourier transform. So you do the fast Fourier transform, which again is just evaluating alpha as a polynomial on a known set of points. And then you do the fast Fourier transform on the other polynomial, multiply them together, and apply the inverse fast Fourier transform to get the answer. Now, to understand this second set of equality, I need to explain what this del diaresis is. And to explain that, I'll go to a slide from a different presentation. It's called a dual or the under operator. It's a dyadic operator. And in the monadic case, you apply G to the argument and then apply after that, and then you apply the inverse to the result. And in the dyadic case, you apply G to the left argument and G to the right argument, and then apply, give them to F, and then apply the inverse. So for example, plus under log is multiplication. That's how the slide rule works, by the way. You take the log of the arguments and then you add them together and then you apply the inverse, which is exponentiation. And lo and behold, it's multiplication. And a more unusual one is a summation is product under exponentiation. So back to the rational. So another way to express this, or these things above, is that you evaluate on a set of points, on the arguments, multiply them together, and then apply the inverse of evaluation, which is interpolation. Or a very short way of saying this is apply the fast Fourier transform on both arguments. And again, fast Fourier transform is just polynomial evaluation. Do the ordinary product, vector product on the result, and then apply the inverse fast Fourier transform. So none of this is new, because people knew that in the 60s. I guess it's kind of new that there's such a short way of expressing that. I encountered a fast Fourier transform in school, in college, and I never grok it. I guess that's the word. I never could understand it, but I think if I had seen this in college, I would have known what it is, because it's so succinct. So earlier I said that the Dyalog implementation is better than the J implementation because I'm older and wiser. That's a joke, but seriously, it's better because of this the contribution by this J user, Henry Rich. He's currently a high school teacher in North Carolina, and in his previous career he did a lot of work with digital signal processing, which uses fast Fourier transform. And he sent really good statement of the FFT to the J forum last December. And I worked with him and we got it down to a pretty good form. So this is the expression in J, and this is the equivalent thing in Dyalog APL. You can actually execute this in Dyalog version 13.0. Not earlier because it uses complex numbers. Because this needs complex numbers to find the roots of unity. So just in the nick of time, complex numbers came in because it made possible this nice statement of the fast Fourier transform and the fast integer multiplier. There are many interesting stories I can tell about this code. One of them is that this function q applies to a vector of length which is a power of 2, and makes a result which is a binary hypercube of reshape of the argument. So how do you do that in Dyalog? Well, you find the log of the base 2 log of the length of the argument, use that to get the appropriate number of 2's, and then you reshape, right? So this is about the best you can do in Dyalog. So for example, if the argument has length 32, base 2 log of that is 5. Right? So 5 reshaped as 2 is 2, 2, 2, 2, 5 times. And you use that to reshape the argument. And then you get a binary hypercube. Well, one of Henry's students, whose name is Marshall Lockbaum, a name I expect you to hear about in the years to come, found a really neat way. Because what you do is you factor the length of the argument. So that's what this cube colon is doing. So what's the prime factorization of 32? 5 2's. And then you just use that to reshape to get the binary hypercube. Does this silence mean that you're not impressed? I was very impressed. This is a high school student coming in after Henry and I have worked on it and found an improvement. Another story that I can tell is that the duo that I was describing is indicated by ampersand dot in J. So it's used actually quite a few times in here. Four times.
So the ampersand dot is, when you say butterfly ampersand dot cube, that means butterfly under cube.
Yes, yes.
So cube has an inverse.
Yes, which I define to be ravel. So there's a way in J to say, well, the system can't figure out, or it doesn't know what the inverse is, so you can declare that for this expression, the inverse is ravel. Okay, so, and the reason why I do that instead of putting the ravel right in this expression is because there's additional insight where you know that, well, I'm doing butterfly under cube, because I'm saying, that I'm doing an under operation. There's some benefit to stating that explicitly that you're doing under. I'll focus on the key function, which is butterfly. It's really very cute because, well, first of all, its argument is the hypercube that we constructed. And then it's doing a for loop, in the J, it's doing a for loop on the rank of the argument, the hypercube argument. So the rank is the log of the length. So if n is the length of x, of the number you're trying to multiply, the multi-digit number you're trying to multiply together, the rank would be the log. And you can verify for yourself that in here, it's doing a linear operation. So each time through the loop, it has to do n operations, and it's looping log n times. So the total time would be n log n. And you can go through the other functions to verify that they're all linear, except for this step, which is n log n. So the total is of order n log n. And the Dyalog APL expression is kind of cute too. Okay. is doing recursion. Rather than doing the for loop, it's doing a recursion using the power operator to stop. So it's R is the rank of the left argument, and it's recursing until the rank is 0. So again, it's n log n. Now, in the presentations earlier this afternoon from England, Adrian Smith said that faster code doesn't matter, you just buy a faster computer. Not true. There's a world of difference between n squared and n log n. So in, I think it was in January this year, somebody sent a message to the J forum saying, why is this so slow? Well, it was an expression that involved multiplying two numbers with over 1 million digits. So 2 million digit numbers. And it took 45 minutes in J. Because J does not yet have this fast multiply. You don't have the school method. And in January, the Dyalog rational numbers implementation was far enough along that I can do the same problem in Dyalog. And it took 8 seconds. So that's 45 minutes versus 8 seconds. So you can't always just buy a faster computer. So these examples just verify that the fast Fourier transform polynomial multiplication works. And it's working with floating point numbers, but you know that the answer is supposed to be integers, so you can just throw them away, throw the imaginary parts away, and round the numbers to the nearest integer if there's any doubt. Yeah, we know this is 0. Okay. So the next thing I want to talk about is another component of rational numbers implementation that determines the performance, and that's integer division. So it's actually quite amusing because it uses you can use Newton iteration to do integer division. So now Newton iteration is normally used to find the root of a function f, and so you have the argument is an estimate for the root omega, and to get a better estimate, you apply f to the estimate, and then you divide it by the derivative of f applied to the estimate, and then you subtract that from the estimate. Okay, and then you apply this defund repeatedly until it converges. You know, and you have to give it an initial estimate, x0. Okay. So to find the reciprocal of f, reciprocal of a number q, let the little f that I want to find the root of be that. Okay, so you can easily verify that if the estimate is actually the reciprocal of q, you get 0. Right? If omega is reciprocal of q, this would be 0. So that would be a root. But then, and so if you let f be that, and you substitute into this equation, this defund, and do some simple algebra, you get that the function you are iterating, this expression, becomes this. So for example, let's say the number that I want to find the reciprocal of is 17, and f is what I said above. And then I apply the power operator from 0 to 7 times on a 1-digit initial estimate of the reciprocal, which is 6. Okay? Scale appropriately. This is what you get. So basically, like all other Newton iterations, when your initial estimate is good enough, the number of correct digits doubles on each iteration. So you don't have to iterate too many times before you get to the correct answer. So how is that an advantage? Well, because you look at the function you're iterating, it's using only integer operations. Because this is multiply. So if you start with an integer and you make sure that in iteration you get an integer answer, you again get an integer estimate. Hopefully a better initial integer estimate. So the function that we're going to iterate, called f1, is kind of like this, but we're going to compute a scale version of the reciprocal of q. So you use a scaling factor which is large enough, the answer is going to be an integer. And this so this S would be the scaling factor. So I'm going to scale up by 60 digits. And I'm going to scale back down on each iteration. So this is not really a divide inside the implementation. It's just a shift, because I'm scaling by a factor of the scaling by a power of the base, or the radix. So here's an example. Here's some new notation. The function rho underbar converts a floating point number into a rational number. So I'm going to use a scale, multiply by s to get a scaled initial estimate. And I'm going to iterate from 0 to 7 times. And again, it's converging to the answer pretty quickly because the number of correct digits doubles on each iteration. Okay. So now I'm going to jump to the next topic, which are prime numbers.
Can I just ask something about that integer division?
Sorry?
Can I just ask something about the
Sure.
integer division?
Yes.
So that's presumably a sort of a basic building block for implementing rational operations.
Yes.
Are you only interested in integer division and getting an integer result, or like the floor of an integer divide?
No, this you can by using a correct scaling factor, you can get you can see that this is going to end up on the bottom, right?
Yeah.
It's going to be 1r something.
Okay.
Right? Or yeah, for example, if you're formatting, and it's if it was that big Fibonacci number we saw before, to convert it to 60 decimal places, this is one of the things you're going to have to do underneath to get the base 10 decimal place display.
So, Roger, excuse me.
Eric.
The row under bar, you said that converts from a floating point to
A rational.
a rational number?
Yes.
If it can, right? Or is it always
It,
convert?
it tries to do the best it can.
Okay.
And
Yeah, I was going to ask you if there was a function to do that, so that's great. And what happens if you have an expression that mixes rational numbers and real numbers? So you add an irrational number to a rational number.
yeah.
What do you get?
I'm going to get to that in a later slide, but you get, it
Sorry,
tries to be, yeah, it tries to be conservative.
Sorry?
It tries to be conservative, so if you have a floating point number, it's all floating from that point on. Okay,
Sorry
so
for jumping ahead.
so that's to avoid rational numbers creeping into your application. That's one of the safeguards, because it's going to be, if you have rationals, then operations will take an order of magnitude more time and or more space, okay, which is, you don't want to stumble into that if you have an application. So for primes, in the teaser earlier this afternoon, I used quad P. So that's the symbol you have to use in the conference edition. But I propose that if and when prime numbers and the prime number function make it into the product, that we use the vertical bar tilde to denote the prime number function. And the mnemonic is that in conventional math notation, the vertical bar with a little slash means does not divide. So that's the mnemonic. So there's a monadic case of prime. Iota 7 gives you the first 7 primes. And you don't have to ask for primes starting from the first one. You can jump around using different indices. Now, lest you think that I thought of this design all by myself, not true. Because it's taken from J, and where did J get it? From Ken. This may look simple to you, but it's a stroke of genius. Because this is a way of getting an infinite vector without using infinite space. So, how so? Because for any index I, you can find out what its value is. So, isn't that a vector? And so the prime function also has a dyadic case, where with a left argument of 1, it does primality testing. So I'll go to my session here. So those are the first 20 integers we shaped as a 2-row matrix. And if you say 1 quad P, so it tells you which numbers are prime, which of the arguments are prime. So 0, 1, 2, 3, 4, not a prime, 5 is prime, 6, 7, 8, 9, 10, 11 is prime, 12, no, 13, yes, 14, 15, 16, 17 is a prime, 18, 19. Okay? Now, when I got off the stage from the earlier presentation, my IQ went back up by 50 points. And the clumsy expression I used before can be done. So if I want to do the primality test 3 times, I just apply it to 3 copies of the argument. Okay? And for small numbers, it doesn't matter, but for big integers, if you're testing for primes, sometimes it can be wrong with a very small probability. But if that's not good enough for you, you just say 1 quad p k reshape of the argument, and then the error probability is raised to the power k. So for example, first let me show you so that's a 50-digit random number. Obviously not prime because it ends in 5. Now there's another case of the prime function. So 4 prime n tells you the next prime greater than n. So m, so I do that, right? And if I say,
why is it the next prime rather than the 4th next prime?
well, okay, good question. The mnemonic is that you go forward to the next prime. You can guess what -4 is. So now if I say 1 prime m, it better say 1, right? Because I claim it's a prime. But the error probability is non-zero. Small, but non-zero. But if that's not good enough for you, you can just say, do that 3 times. And if one of these is 0, then you know that hell has frozen over. But since they're all 1s, yeah, they're all 1s, and the primality test is independent. They're independent tests. So the error probability is cubed in this case.
So the non-zero probability is because of the algorithm that you're using,
yes,
right, which is a fast algorithm. Do you have any
yep.
way to force it to a slower algorithm that guarantees that the answer is correct?
There is a way, but you have to wait quite a while for the answer.
It's a while, so hell freezes over.
How old is the universe? So in exchange for the non-zero probability of error, you get a quicker answer. Now, I'll tell you something that my thesis advisor told me years and years ago, which I have never forgotten. The mathematicians may object to this. Well, what is this probabilistic algorithm? But my thesis advisor's point is that we're running our code on a device that depends on quantum effects. So you think you have a deterministic algorithm that always works. Well, as I speak, cosmic rays are raining down on us,
I understand.
and it doesn't have a 0 probability of error either.
No, I was just curious
Yeah.
as to how long the method that guarantees a proper result would run. I know this is extremely fast,
Yeah.
but are you talking about thousands of years, or what are you talking about?
Well, it depends on how big a number you're testing, right?
Right.
I think for 50 digits, you may get it in hours. But yeah, but you could be working with a million digits, right? So we saw this already. This is testing a number, and it says it's composite. So another case of the prime function is using a left argument of 2. It's factoring. It's doing the prime decomposition of the argument, returning a 2-row result. So that's the mnemonic, 2-row result of all the distinct prime factors and the exponents. So 1, 2, 3, 4, 5 is 2 to the power 6 times 3 to the power 1 times 6, 4, 3 to the power 1. I should say all the slides on the memory stick that you got from when you registered. And the 3 case down here is again prime factorization, but with the prime factors listed as many times as necessary and listed in sorted order. And of course, if you multiply them back together, you should get the original number back. You see a dual here? So 3 prime and times reduced are an inverse pair. There's actually an amusing under expression where you do some f under factoring. And again, 4 finds the next prime larger than the argument. So the next prime after 29 is 31. The next prime after 25 is 29. So let's do a biggish number, factorial 35 as a rational number. And you find the next prime after that is that. And minus 4 prime gets you to the next prime smaller than the argument. So these 2 primes bracket this number. And one more, well actually 2 more. The 10 prime, 0, 10 means the Boolean vector which tells me which of the numbers between 0 and 10 are prime. So 0, 1, 2, 2 is prime, 3, 4, 5, 6, 7 is prime, 8, 9. Okay? And you don't have to start from 0, you can start from some big number like 10 to the 30. So 0, 10 plus that will be 10 to the 30 and 10 to the 30 plus 100, which numbers are prime. So there's 1 there and 1 there. Now this is not available in the conference edition because I wasn't able to get to implement the inverse of quad p or the inverse of the prime function. But the prime function on 3142 gets you the primes whose index is 3, whose index is 1, whose index is 4, whose index is 2. Okay? So the inverse on 7, 3, 11, 5 should get you 3142 back. And for coding convenience, now this part is implemented in the conference addition, which is the prime function with our left argument of -1. Gets to the, is actually the number of primes less than the argument. In conventional math notation, it's usually denoted pi of n. It's the number of primes less than n. And if your choice is to use quad IO1, it would honor that. And the function is then the number of primes less than or equal to the argument rather than less than the argument. Okay, so for example, the number of primes less than 100 is 25, and the number of primes less than 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So this is a summary of the new notation introduced for rational numbers. So for rational constants, you put a little r between the numerator and the denominator. And there will be a new quad variable, which is not implemented in the conference addition, but it's intended to be a safeguard so that you have to assign 1 to quad rat in order to get rational numbers. To avoid rational numbers creeping into your application by accident and slowing down by an order of magnitude or using an order of magnitude in space. And there's a new function, another new function called quad, denoted quad Q in the conference addition, but could be row underbar eventually, is to convert ordinary numbers into rationals. And it's self-inverse, it converts rationals back to ordinary numbers. And this may disappear, but it converts strings to rationals. This was implemented at a time when I wasn't able to enter rational numbers directly into the interpreter.
What would 1.5 space 2R3?
Well, let's see. 2R3? No answer. Ah, good answer. Thank you, Jeff.
Sorry. I do apologize.
But, yeah.
What should it be?
Probably should be floating point or error, because this we don't want rationals to be introduced by accident into your application, leading to those dreaded phone calls in the middle of the night. Right? Yes.
Please, what's the depth of a rational number?
The depth.
Yeah.
Okay, you found a part that doesn't work so well right now.
Actually, you might should test 1 equals 1R1.
Yeah,
0.
yeah, yeah. It's for all those cases to work, rationals have to be implemented as a proper data type in the interpreter. Currently, it's not. So the functions work, but it's not a proper data type, and you can see rough edges, even crashes if you know what to do. So I propose also to have a quad rat PP which if 0 would use the R notation in display, and if it's not 0, you will specify the number of digits in the display. So we saw that a little bit of that earlier, because when I did 1/4 to the power 1,000, right? It's hard to know just at a glance how big that is. You know, is that bigger than is that bigger than 2R3 to the oh, sorry, 1R3 to the, where did you go? Okay. Holy cow. Where did the cursor go?
You hit down pause.
Sorry?
Pause.
Pause, okay. Yeah, okay, so 1R3 to the power. Yeah, so which is bigger? So that quadrat PP, let me see. Oh, okay. So if you're doing just one off, you can say minus 60 thorn. Oops. Or too many digits, I don't need that many. 30. Okay. So if you're just doing one operation, you can just apply the thorn to it. But if you're working with lots of these, well, one of the advantages of APL is that you don't have to say explicitly, I'm going to format this or whatever. So that quad PP is a way to change the default display so that well, let's ask for 30 digits. So now if I say X, or I get the kind of output that's more convenient for this kind of thing. Okay? So let me turn that back. Okay, the more notation. The prime function, again, in the conference edition is indicated by quad P. And the monarch case tells you the n prime. And it's sensitive to quad IO. And -1 is the inverse function. And because this is sensitive to quad IO and this is supposed to be inverse, it too is sensitive to quad IO. And 0 prime n is the function is n composite. 1 is n prime. 2 is a factorization of n as a 2-row matrix result. And 3 is the prime factorization as a list. And 4 going forward from n is the next prime larger than n. And of course, -4 then has to be the previous prime less than n going backwards. And then 10 prime m comma n is the sieve for the integers from m to n minus 1. It's a Boolean result. 1, 0. The mnemonic is 1, 0. Get it? So the prime function is modeled as a defund that you can get. I think either by loading the defunds workspace or getting it from this URL.
How about imaginary numbers? Do they mix, imaginary numbers, do they mix well with rationals? Can you have a denominator that's,
No, you cannot. Yeah. It's actually one of the questions I'm going to ask now, actually. So Goodley, and so we still have an open problem in Dyalog. So oh.
It's actually dinner time, guys.
Oh, okay. I'm sorry. Okay, just one question then. Because this is an important open question. Because when you mix flows with rationals, it's pretty clear it should be rational. And when you mix integers with rationals, it seems good to have a rational answer. The problem is that in Dyalog APL, the integer could have come from demoting a floating point. So now we have a problem of what to do. So it's something that we're still fighting over. So I don't want to keep us all from dinner, so that's it.